This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on work problems in calculus, tanks. Let's remember, of course, that work is force times distance. So the change in work is this variable force f of x times the change in distance. If we have a constant force, then the constant force times the constant distance gives us our work, but that's not terribly interesting. So our total work is the sum of all the change in works, all the small pieces. So it's the sum of the f of x times change in x. And then we shrink change in x to 0, and this becomes an integral. So our formula for work for a variable force is work is the integral from a to b, whatever that interval is, of that force function f of x dx. And we're going to look at situations where we are pumping fluid out of tanks. So here's our first example. We have a cylindrical tank. It has a height of 10 feet and a radius of 7 feet. It is half filled, so that's up to the 5-foot level. Find the work necessary to drain the tank by moving all of the water out of the top of the tank. So let's have an image to work from. Cylindrical tank, 10 feet high, half filled, filled to the 5-foot mark. We want to find the work necessary to move all of the water out of the tank. Well, frankly, you have a choice on how to set up your number line here. I'm going to choose to put 0 at the top. You could choose to put 0 at the bottom. I tend to prefer to put 0 at the top unless I am pumping it out of something other than the top of the graph, which you'll see in some later examples. So I'm going to call 0 the top of this cylindrical tank. We want to drain everything out. We're going to focus on this piece, this little disk of water, which height is at this value, and we're going to pump that out. So we need to determine what the force is and what the distance is. So we're going to start with the area of a circle. Area of a circle is pi times the radius squared. Looking at this, the radius is always the same. The radius is always 7 feet. So the area of my circle is pi times 7 squared, or 49 pi square feet if you're keeping track of units. But I need volume. So this is a disk. It is a circle with thickness. And the volume of that disk will be the area of the circle times the thickness. The thickness I have listed here on my picture. Just call it the change in x as that is moving. So the volume of the disk is the area of the circle, 49 pi times the change in x. Remember, we're looking at work. Work is force times distance. Volume is not force. So we need to figure out some way to convert that. So here's our information. There's our graph again. There's our volume of the disk is 49 pi times the change in x. We're dealing with British units here. In that case, the density of water is 62.5 pounds per cubic foot. What I have here is in cubic feet. So we can convert from volume to weight. So the weight of the disk will be the density in pounds per cubic foot times the number of cubic feet. So the weight of that disk is 62.5 times 49 pi times change in x. Density times volume is the weight. Now the nice thing about British units is weight is a force. Weight is a force. In metric, we tend to work with kilograms. That is a mass, that is not a weight. So we'll need to deal with that separately. Okay, let's remember that work is force times distance. And like I said, weight is a force. So the force we're dealing with here is 62.5 times 49 pi times change in x. And then the question is, what is the distance we have to use to pump that out? Now, I've set the scale starting at 0 at the top. So this is 0, 1, 2, 3, 4, 5 is the water line, halfway filled. 6, 7, 8, 9, 10. I'm calling this at a value x. That's x units from 0. So that will be the distance I have to pump it out. If I'm calling this 0, 1, 2, 3, 4, 5, 6, x, x is the distance it'll take to pump this out of that cylinder. So again, the distance to move that disk out of the water is x sub I. We're saying this is a specific disk in that tank. The distance to move that specific disk out is x sub I. Now the work to move that out, again, is force times distance. Here's our force, our weight, 62.5 times 49 pi times the change in x times the distance. The distance is x sub I. Force times distance. Force is the weight, distance, how far does it take to go out of the tank, x sub I units. So this is the work for just moving out that little disc out of that tank. But you'll notice we have discs all along here. And what are the x values, the distance from here? What are the x values for all of those discs of water? What do they range from? They range from 5 to 10. And that's going to be important for us to look at. So our total work is the sum of all those discs. Imagine an infinite number of very, very small discs here. And we're pumping all of them out. So the total work is the sum of all of the little discs. But then, of course, we're going to shrink that change in x to 0 and go from a sum to an integral. But we know x ranges from 5 to 10. Why is that? We said the cylinder was half full. It's 10 units. From the top to the bottom, it's 10 units, so it's 5 units high. The ranges where the discs are going to occur are going to be values where x ranges from 5 to 10. So our x values here will indeed be 5 to 10. So we want to convert that somehow. As we shrink delta x to 0, this sum is going to become an integral from 5 to 10 of the force, 62.5 times 49 pi times the distance, which was just x, dx. What's nice about this is 62.5 and 49 pi are constants. They can come out in front of the integral. And all I'm doing is integrating x from 5 to 10. The integral of x, of course, is x squared over 2 from 5 to 10. 10 squared over 2 minus 5 squared over 2, which is going to give us what? 100 over 2 is 50 minus 25 halves. So 50 minus 25 halves, or 100 halves minus 25 halves is 75 halves. And let's multiply all those together to get an approximation. And you'll notice I just kept 3 digits of interest. I have 62.5 only gives me 3 digits, significant digits, if you will. So I really shouldn't go beyond that. That's not going to quite be right. So we're just going to go ahead and keep 3 significant digits and say 361,000 foot-pounds is the total work to pump out that tank. It was half filled. The total work to pump out that half is going to be 361,000 foot-pounds. So that was a question in British units. The next one is going to be in metric. So let's look at this. How much work is needed to pump all of the water out of a cylindrical tank that has a height of 10 meters and a radius of 5 meters if the water is pumped to an outflow 10 meters above the tank? So I have an outflow and I also have metric. So there's 2 changes from our first example. When I have an outflow that's above the tank, I prefer to put the 0 at the bottom. So for this analysis, I'm going to call this a y value of 0. Just change the letters. The entire tank is full. It is a 10-meter tall tank. So from 0 to 10, we're filled with water. The outflow is 15 meters above the tank, obviously not to scale. So this is 10 meters, this is 15 more to get ourselves a decent image of how this is working. But the analysis is essentially the same. We need to figure out what the force is for this, but we're going to start with area. So the area of the circle is pi times the radius squared. Like the last example, the radius for this problem is constant. The radius is always 5 meters. So the area of the circle is pi times the radius squared. The area of the circle is pi times 5 squared. 25 pi is the area of that circle. Now we need volume. The volume of the disk is the area of that circle times the thickness. The thickness here is change in y. So the area of the circle is 25 pi. The thickness is change in y. So the volume of the disk is 25 pi times change in y. We have volume. Work is force times distance. We need to think how we can convert volume into force in the world of metric. Well, first we're going to go to mass. Mass is density times volume. And you may know that we have 1 gram per cubic centimeter. And that can be converted to 1,000 kilograms per cubic meter for water. Different fluids will have different densities. So you'll notice when we're dealing with British units, we said 62.5 pounds per cubic foot. 1,000 kilograms per cubic meter is what we have here for our density of water. Now, we can convert the volume to mass, multiply the density times the volume, we'll get mass. Fine. 25 pi delta y, volume times the density times 1,000. Fine, we have the mass of the disk. But is the mass a force? We can convert it into a force by using Newton's law. Newton's law is F equals ma. And on the surface of the Earth, the gravitation constant, the acceleration is 9.8 meters per second squared. So I have mass. I can convert mass into force by multiplying by acceleration. So the force is this mass that we have up there, 25 pi delta y times 1,000 times a times 9.8. And our units, kilograms times meters per second squared, is a Newton, if you want to keep that straight. So we've done our work here for this metric question. We've converted it into a force. And work is force times distance. We need to figure out how far we've got to go ahead and pump this out of the cylinder. So if it goes to the top, that's how much? Well, this is 0, and this I'm calling as y sub I. So from y sub I to 10, if you start at y sub I and you go to 10, that would be 10 minus y sub I. But we have another 15 meters beyond, so a very, very high spigot 15 meters beyond this. So if I'm starting at y sub I and I want to get to 25, how far do I have to go? 25 minus y sub I. For example, if y is 7 and I have to end at 25, 25 minus 7, it's got to go 18 meters to exit. So the distance that I have to travel from this disk is 25 minus y sub I. And frankly, that may be the most challenging part of the problem. So we have our force and we have our distance. The distance to move this piece out, it's at a height y sub I from the bottom of the tank to get to the top of the tank. The distance to move that out of the tank is 25 minus y sub I. So we need to go ahead and set up our integral to find the total work. Work again is force times distance. This is our force, that is our distance. So that is the work to move just out that one disk of water. I'm calling that change in work for that one little itty bitty piece. A small change in x is going to correspond to a small change in work. But the total work is the sum of all those changes in work. I've got to add all of these up. Well, you know how we're going to do this. We're going to wind up shrinking delta y to 0, and that's going to convert that into an integral. But we need to think about what are the values of the integral that we need. What are we ranging from? So again, this is where we're at. This is our total work is the sum of that stuff. And here's what we're looking at. We have to ask ourselves, what are the values of y sub I? What does y sub I range from? In our first example, the tank was half filled. This tank is completely filled. We're taking a completely filled tank and we are draining it. So what are my y values going to correspond to in this problem? Anything from 0 to 10. Y will range from 0 to 10. So knowing that, as we shrink delta y to 0, this is going to become an integral. The integral from what? From 0 to 10 of all of that, and the delta y becomes a dy. So now our challenge is to evaluate this integral. 25 pi is a constant, 1,000 is a constant, 9.8 is a constant. Move all of the constants out in front of the integral operator. And we're down to the integral from 0 to 10 of 25 minus y, antiderivative 25y, antiderivative of y squared over 2, evaluated as y goes from 0 to 10. Plugging in y, 25 times 10, minus 10 squared over 2. Plugging in 0, of course, 25 times 0 is 0. 0 squared over 2 is 0. 250 minus 50, I think, is what we're going to get there. 250 minus 50 is just 200. Multiplying all that together, I went a little beyond. Maybe 1.54 times 10 to the 8th would be better, but I've gone ahead and giving you an idea what the answer is, approximately 1.539 times 10 to the 8th. Now our units here, force times distance in metric. Force is a Newton, distance is a meter. A Newton times a meter is a joule. So our units for this problem are joules, 1.539 times 10 to the 8th joules, a lot of joules. One more question for us to look at. This is one that's often done in calculus classes. Here we go. A conical tank with a point down has a radius of 5 feet and a height of 12 feet. The water level in the tank is 6 feet higher than the bottom of the tank. Find the work necessary to empty the tank if the outflow is 5 feet above the tank. So again, we have an outflow above the tank, so I'm going to make the bottom 0 again on this example. Call the bottom 0. The water level is 6 feet higher than the bottom of the tank, so from here to here is 6 feet. Notice we're back to British units. It has some advantages in these problems because weight in British units is a little easier to find. So what's happening here, though, in our first two examples we had cylindrical tanks. This one's a conical tank with a point down. Now, you'd never build a tank this way, so it's a little artificial, but it's a nice mathematical example. So let's take a look at it. The radius changes as we move up and down this cone of water. So yes, we know that the area of the circle is pi r squared. But unlike our first two examples, the radius changes. So we need to be able to figure out some sort of a relationship. So I'm calling y sub I the distance from the ground, the distance from the 0 point. So what I'm going to create here is something to enable us to do that. So as the water level rises, as y sub I increases, the radius changes, and we need to figure out some way to describe that. So here is our original picture. And again, the area of the circle is pi r squared. But I can actually take a look at some similar triangles. Let's take a look at this. 5 over, 12 down, r over, or here, r over, y sub I down. So 5 is the radius, 12 is the height, r is the radius, y sub I is the height. So I can set up similar triangles. 5 is to 12 as r is to y sub I. So as y changes, the radius changes. The similar triangles enable us to do this analysis. So I want to solve for r. How does r change as a function of y? Well, multiplying by the common denominator of 12yi, we get 5yi is 12r. Remember, I want to solve for the radius. Divide both sides by 12. And I get the radius is 5y sub I over 12. As y sub I changes, the radius changes. And you might think, what are the values of y sub I? What does y sub I range from? Remember, we said it was 6 feet higher than the bottom of the tank. All right, but back to our discussion here. Area of the circle is pi times the radius squared. So the area of the circle will be pi times 5y sub I over 12 squared. So that's the area of the circle. We have to convert from area of a circle to some sort of force. In British units, weight is a force. So there's our picture again. There's the area of our circle. The volume of the disk, we perceive this as a disk of water. The volume of the disk is the area of the circle times the thickness. The thickness here is change in y. So there's the volume of our disk times the thickness. That gives us the volume. Now, how do we go from volume to weight in British units? Well, that's not terribly difficult. We know weight is density times volume, and we know we have 62.5 pounds per cubic foot. So we're able to define the weight of this little disk of water, and weight is a force. So if we have the force, we need to think about the distance to pump this out. So let's take a look at our picture again. This time I called 0 the bottom. Y is our level of our disk. It has to get to 12 to go out, and then it's got to go 5 more because the spigot is 5 units above the tank. So 0 to 12 to the top of the tank, 5 units to get to the spigot. That takes me to 17. I'm starting at y and I'm going to 17. What is the difference starting at y going to 17? Hope it's obvious. That's going to be 17 minus y. So the distance to move that out, 17 minus y. Again, the difference, starting at y, ending at 17, the difference is 17 minus y. That's our subtraction. Work is force times distance. We're starting with this one little disk of water. Force times distance. There is the force. Weight is the force. There is the distance. We put those together. Force times distance is the work to move that little disk out of that cone. Now we need to simplify that, eventually go from work of a single disk to all of them. So the total work is the sum of all those little pieces. So it's the sum of all of those guys. But we need to figure out where does y range from. So this was in a sense half-filled, not in terms of volume, but in terms of height. So this was 0, this was 6. So my disks that I'm working with are all going to range from 0 to 6. As I shrink del to y to 0, this will become an integral. So y ranges from 0 to 6. As we shrink del to y to 0, we get the integral from 0 to 6 of 62.5 pi 5y over 12 squared times 17 minus y, and del to y becomes dy, as our limit of a Riemann sum becomes an integral. So all we've got to do now, we've done the hard part. Setting up the integrals is the hard part. Let's go ahead and evaluate it. So 5y squared should be 25y squared. Let me fix that. So that's fixed. I just pulled the 62.5 pi out to make it a little easier. Integral from 0 to 6. 5 squared is 25. Y squared is y squared over 144 times 17 minus y dy. So we'll notice 25 over 144, also a constant. So that can come out as well, leaving y squared times 17 minus y. Distributing here, 17y squared minus y cubed. Antiderivative, 17y cubed over 3 minus y to the 4th over 4, as y ranges from 0 to 6. Plugging in 6, 17 times 6 cubed over 3 minus 6 to the 4th over 4, minus plugging in 0, 17 times 0 cubed minus 0 to the 4th over 4. And what do we get? This piece simplifies into 1224. This piece simplifies into 324. That goes away. Those are zeros. That subtraction, of course, gives us 900. And all we have to do now is go ahead and multiply that stuff out to get an approximate solution. And what do we get? We get approximately 30,700. Again, I stuck with 3 significant figures this time. 30,700 foot-pounds approximately. And that will conclude this lesson.